Okay, first of all, I'm going to apologize if you guys hear any bells in the background. Um, Recording this at school, and the bells are on a slightly different schedule today, so if the bells go off and you hear it in the recording, I apologize. Okay, first thing, wrong section. Let's cross that off. This is actually section 10.5. Conic sections. Hopefully you've been exposed to some conic sections here. More than likely it would have been in pre-calculus. If not, this is probably one of the more important things that we're going to do that's something really not covered in calculus, but it is extremely important for Calculus 3. So this is a really important one. Um, the homework for this in particular lesson is actually going to be in class. It will be assigned when we get to that point in time, so I'm not going to write the homework down. There is a relatively extensive um, number of problems to do in this section. Again, very important that we understand this, which is why we're doing it. Okay, let's start off with one of the conic sections. First of all, conic sections. Conic section comes from the word cone, conic cone. Um, every one of these sections can actually be developed by taking a plane, an actual geometric plane, and slicing through a cone. So if you think of, I'm going to try and sketch this at the top here. You think of we're actually going to make this a double cone. If you think of a cone, it looks like that, and you take a plane, if you slice it in various different ways, you're going to get these conic sections. So one of the ways to slice a cone is to slice it perpendicular, or perpendicular to the top. If you slice this thing perpendicular to the top, and then you were to look at its cross section, what you would get is a circle. There was a bell, I'm not sure if you heard that. If you take a plane and you were to slice it parallel to one of these axes, so this is the axis right here, and this is another axis right here. If you were to slice it parallel to that, it would look something like that. And when you slice it parallel, this is really difficult to see, the shape that it makes right here, and if you kind of circle it to the other side, that's your parabola. And then if you were to take one and you were to slice it straight up and down, so it would look something like that, and then you would create your plane. Well, that's going to form right here, right here. Whoops, I got that upside down actually. It'll look something like that. Let me get rid of that. Hold on. I'll actually form something like this, and like this, and that's going to be your hyperbola. Okay, you can form other different conic sections as well. If instead of going completely parallel, it's going to be hard to do. Let me see if I can pick another color here. Instead of going completely parallel to the top, like the green one is, if you just slightly angle it so that it comes through at, let me see if I can do this towards the bottom, at this kind of an angle, so it actually cuts through both sides of this cone right here. Well, what's going to happen now, instead of a circle, because it's tilted, it's actually going to form your ellipse. I know this is not the easiest thing to see here, but we're going to deal with a lot of these three-dimensional figures throughout the course. So that's just kind of an overview of the four basic conic sections: circles, ellipses, hyperbolas, and parabolas. You can also form a line if your plane simply is one of the axes. If the plane actually goes right here, that forms a line. If it cuts right through the center, right here, it is simply a point. So all these different geometric figures come from a cone, a double cone as a matter of fact. Okay, parabolas. Let's get to this. Parabolas, the definition of a parabola. It's a set of points in a plane that are equidistant from a fixed point F. And we call that fixed point, you've probably heard this before, the focus. And a fixed line, which is called the directrix. Apologize for my awful penmanship there. Okay, so a parabola is a set of all points in a plane that are equidistant, or the same distance, from a fixed point, which we call the focus, and a fixed line, which is called the directrix. So every point in the parabola will be the same distance from that point and that line. For a parabola with a vertex at the origin, the focus of the point is the point 0, p. Notice that there's a p-value, which is the y value. And the directrix is the line y equals negative p. That should really make sense if what we just said was every point on the parabola has to be an equal distance from the focus, which is a 0p, and the directrix, which is y equals negative p. P and negative p should be the same distance away from the origin. Using this information and the distance formula, it can be shown that the equation of the parabola with the focus 0p and the directrix y equals negative p is x squared equals 4py. That's kind of the equation that's given, more commonly seen as y equals 1 over 4p x squared, where 1 over 4p is going to be the coefficient of x squared. All right. Likewise, if the parabola is symmetric to the x-axis instead, the equation becomes x equals 1 over 4p y squared. And the focus of the directrix is p0 instead of 0p, and x equals negative p is going to be the directrix line. All right, so we're going to show these two things graphically to hopefully make more sense. Okay, so let's go ahead and just sketch a parabola. Something like that. So the idea is there is a focus at the point 0p, and I'm just guessing here. Whoa, that's way off. Something shifted there. Give me a second. All right, let's see if I fixed it. So we got a point. Still not the best, but we'll deal with it. There's our point 0p. And then down here, if I take about the same distance away, maybe right here or so, it's close. This would be the point. This would be the equation y equals negative p. And hopefully, if I've done a semi-decent job, and again, this is just a sketch, what you would see is that any point that I pick, let's pick a point up here, any point on the parabola, if I were to measure this distance here, and I were to measure this distance here, it's not, but it should be exactly the same. These should be exactly the same distance. I didn't do an extremely good job with my drawing, but that's the general idea. And any point, this point right here, wow, this point right here should measure the same distance. All right, if we go with the second option, x equals 1 over 4py squared, man, this is going to take some getting used to here. it's going to have to do. And if I were to draw my focus, maybe about right there, that wasn't bad. The directrix then would be about right here. X equals negative P. Man. There, it's better. And this would be our point P0. And that would be our focus. So once again, the distances from any point on the parabola to the focus should be the same distance to the directrix. All right, there's the idea. Spent way more time on that one than I really wanted to. Hopefully that gives you a semi-decent visual of it, though. All right, so what we want to do is we want to find the focus and the directrix of the parabola, which is given to us as y squared plus 10x equals 0, and we want to sketch the graph. All right, so the first thing we need to do is we need to put this in a more familiar form. First of all, I see that the y is squared. That tells me automatically that I'm going to solve for x, and by that, I know I'm going to have a sideways parabola. So we're going to solve that equation for x. We're going to subtract y squared and divide by 10. So we should have 10x equals negative y squared dividing by 10. We get negative 1/10 y squared. What that tells me, because I know that this negative 1/10 is the coefficient, that's equivalent to 1 over 4p from the previous page. Negative 1/10 is 1 over 4p. Okay, and the importance behind that is the fact that now I can actually find p. I can find the point for my directrix and my focus. So, little cross multiplication gets us 4p equals negative 10. So p then equals negative 10 over 4, or reduced as negative 5 halves. And if you recall, the focus is going to be the point, since it's sideways, it's going to be an x value, negative 5 halves, 0. The directrix, therefore, is going to be a vertical line, which is equal distance away from the origin, so it's going to be x equals the same distance away from the origin would be positive 5 halves. So now I pretty much have everything I need to make a sketch. So let's see, we can put this right here. Looking at my equation, x equals negative 1/10 y squared, that actually tells me that this thing is going to open to my left. If we weren't sure about that, if you plot your focus at negative 5 halves, so let's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, that's really all we need. We don't need anything on the y-axis here. Negative 5 halves 0. Negative 5 halves is negative 2.5. So that'll be right about here. X equals 5 halves is our directrix. Positive 2.5. Right there. And then if I go ahead and sketch the parabola, it looks something like that. And again, every point on that parabola should be equal distance away from the focus and the directrix. All right, that is a parabola. We're going to move on to an ellipse. And most people know the ellipse just as being a stretched circle, and that's really technically what it is. More to the point, a circle is an ellipse where it's not stretched and every single point is equal distance from the center. So an ellipse is the set of all points in a plane, the sum of whose distances from two fixed points, which are not called a focus, they're called foci when there are multiple of them, is constant. So again, basic idea is whatever the ellipse looks like, every point on the ellipse, if I add the two distances from each foci to that point, everywhere on the ellipse it's going to be the same. Again, I'll do an illustration at the bottom to kind of show you. So for an ellipse centered at the origin, the foci are equidistant from the origin and can be found by using the equation b squared equals a squared plus c squared. If you really think about it, that comes from the Pythagorean theorem. If you were to add c squared to both sides, you would get a squared equals b squared plus c squared, very similar to the way we do it. C is the distance from the origin to the focus, A is the distance from the origin to the ellipse along the major axis, and B is the distance from the origin to the ellipse along the minor axis. Again, we'll take a look at all that when we get to this sketch. The general equation for an ellipse centered at the origin with a major axis along the x-axis is given as x squared over a squared plus y squared over b squared equals 1. An ellipse with a major axis along the y-axis, very similar, but the b squared is under the x squared and the a squared is under the y squared because the a and the b represent the major and minor axes. So in general, the graph of an ellipse will look something like this. Whoops. All right, let's see if I can do this. Not too bad. All right, so here's what we were talking about. The vertex, whoops. Try that again. Vertex on the major axis being the longer axis, is going to be given as a0 and negative a0. It's weird how it's doing that. It's got some kind of issue over here for some reason. Not sure what's going on. It's distorting. Have to figure that one out. Okay. And then the minor axis, 0, b, 0, negative b. And then we have the foci, which are located someplace within the ellipse. May not be exactly equidistant from the origin to the vertices. It's probably not, as a matter of fact. But the idea is, first of all, this is negative c0. This one is c0. The idea is, if I were to pick any point, and I'll pick it right, man, it's really not liking me switching these pens. If I were to pick any point right there, the distance that I take when I add that one plus that one is going to be exactly the same as if I pick any other point. I could pick a point right here. If I were to take and add the distance from here and the distance to there, they are exactly the same. So the sum from here to here to here is exactly the same as it is from here to here to here. So every point on the ellipse, if you take the distance from the foci to that point, it's gonna, and you add the two distances of both foci to that point, it will be the same everywhere on the ellipse. And that's how an ellipse works. All right, so what we want to do here is we want to sketch the graph of the ellipse, which is 9x squared plus 16y squared equals 144, and we want to locate the foci. All right, so first thing we want to do is we want to put this in standard form. What you should see with this is not in standard form because the right side does not equal 1. Well, let's make it equal 1. Let's divide everything by 144. If we do that, dividing both sides by 144 and simplify, we get x squared. See, 9 goes into 144 16 times, so that'll be over 16. Well, that makes the next one easy. Dividing 144 here makes it over 9 equals 1. Okay, that makes it easy to see. First of all, the larger axis is under the x. Therefore, we know that the major axis, or the stretched part, is going to look more stretched on the x-axis. And we know that a, because the original equation is x squared over a squared, has to be 4, since the square root of 16 is 4. That makes b, which is the minor, because it's under the y, the square root of 9 is 3. All right, so we can go ahead and do a sketch. Okay, it doesn't have to be perfect. Let's see, 1, 2, 3, 4. I only need to go 3 on the y, 4 on the x. So if I've done this correctly, let's see if it likes this or not. Let's see if I can get this to go through. That's not bad. All right, there's our sketch. And what we need to find is the foci. We need to find the c values. The c values are going to be the two foci within the ellipse there. And if you remember, the equation for that was c squared equals a squared minus b squared. All right, I really am having a hard time with the left side of this screen for some reason. So for right now, we're going to keep it on the right. C squared equals a squared minus b squared. And obviously, if you did that backwards and you did b squared minus a squared, you'd get a negative number. Ellipses do not involve imaginary numbers at this point. So let's go ahead and fill this in. C squared is going to equal 16 minus 9. C squared equals 7. Therefore, C is going to equal plus or minus the square root of 7. So my foci are going to be negative square root of 7, 0, and positive square root of 7, 0. Square root of 7, I'm not exactly sure, someplace in between 2 and 3. So we'll go out here, 2 to 3, someplace out in this general range. Probably a little bit closer to 3 than it is to 2. And there would be your foci. C1, C2. All right, let's say instead we are given the information that we want to find an equation of the ellipse with foci and vertices given to us. So now they're giving us that information. We want to be able to write the equation from it. So the first thing we should notice is, okay, the foci and the vertices are both on the y, which tells me that, all right, sorry about that. I had an interruption. Had to come back to it. So again, looking at this, we can tell that the major axis is on the y-axis. So we know that A, because it's always going to be the location of the major vertice, which is given to us, we know that, it's also going to be on the same axis as the foci. So we know that the major axis is on the y-axis. A is going to be 3. And C, because it's the location of the foci, is going to be 2. So we need to find B, because we do need to find the location of the minor axis. So in order to find B, we're going to use the same equation we did before, starting off with C squared equals A squared minus B squared. But we need to solve that for B instead. So adding B squared to both sides and subtracting C squared gets us that B squared equals A squared minus C squared. So now we can find B squared. So B squared is going to be 9 minus 4, or 5. So B is plus or minus square root of 5. Now we have everything we need to write our equation in standard form. Remember in this case that the y is going to be the major axis, so y gets the A on the bottom and the x gets the B on the bottom. So our equation should look like x squared over b squared, squaring the square root of 5 is 5, plus y squared over a squared is 9, equals 1. Now if you go to look in the book, maybe it's not written in this way, maybe they wrote it the way that we gave it in the previous problem above, which is basically taking and getting rid of the fractions. So if we get rid of the fractions, we're going to multiply by the common denominator, which looks to be 45. Multiplying everything through by 45 would give us 9x squared plus 5y squared equals 45. And either one of those are perfectly acceptable answers. Just depends on what form they're looking for. All right, there's the ellipses. We still have hyperbolas and shifted conics to do. So what I think we're going to do, because this video is running long, is we're going to stop this video here. We're going to pick it up again and finish it off with hyperbolas and shifted conic sections. All right, so we'll be back with another video.